So this is the 2010 Mechanics paper for Level 2 Physics. Question 1, throwing the discus. Part 1. James is preparing to throw a discus by swinging it in a horizontal circle. The diagram below shows the path of the discus moving clockwise as seen from above. So we would presume that James is standing right in the centre and his arm is attached to the outside of the discus as it rotates around. A. Draw two labelled arrows on the diagram above to show the velocity. Remember, it says two labelled arrows, so don't forget the labels, to show the velocity and acceleration of the discus at the instant shown. We need to change colour because I've already drawn on this. So the velocity at the instant shown is always at a tangent to the direction of rotation on the circle, or tangent to the surface, or at right angles to the radial direction. And we have to label it, remember, the labelled arrows, so that's going to be, we can label it V, or probably better to write velocity. And the other one, the acceleration is towards the centre. That is so fundamental to circular motion. And if you don't know why that is, you better go and watch those particular videos. B. James releases the discus at the position as shown in the diagram below. Draw an arrow showing the direction the discus travels. Explain why the discus then travels in the direction you have drawn. So at the instant shown, it's got its instantaneous velocity, and in the absence of any force acting on it, it will continue at that velocity, which means at that speed and in that direction. And again, the instantaneous velocity is at a right angle from the radial direction, or from James releasing it. Okay, so explaining why the discus travels in the direction, I think I sort of did just there, but if we consider the forces, there are no forces, no unbalanced forces to cause acceleration, and an acceleration is required to change the direction. So acceleration is required to change direction. DIR, little n for direction. Anything else of importance? No, I guess you could say a little bit on the end, hence it travels in a straight line, hence goes in a straight line. There we go. Moving on, trying to keep it fast. C. Before throwing the discus, James swings it around in a horizontal circle at a constant speed of 11 meters per second. Let's write that down because it's going to be important. 11 meters per second. The mass of the discus is 2.1 kilograms. That's going to be important. 2.1 kgs. And at one time he applies a horizontal force F of 290 newtons to it. Calculate the radius. Radius equals question mark of the discus circular path. Okay, so drawing the diagram, James is swinging it around. Here's the discus. We've got the radius here. He's applying a force towards the centre. Has an instantaneous speed, which is the 11 meters per second that we're talking about there. And the mass of the discus equals whatever it does over there, 2.1 kilograms. So that force applied to the centre is the centripetal force. You might have seen an equation representing it before, mv squared over r, which has all of the factors we need except for the r, which is the only one that's unknown, which we need to find out. So we rearrange this for r, so it'll be mv squared over f, and we just substitute those in. Mass in the top, 2.1, times by v squared, which is 11 squared. Don't forget the squared, everybody tends to do that, or a lot of people do that. Divided by the f, which is 290, and that gives you a radius of 0.88 meters, according to the marking schedule which I'm reading off. There you go. Nice, quick, fast one.